one, which of the following EM goes from lowest energy? Now the lowest energy is radio, so that's kind of a good part. But radio jumping to X-rays is too extreme. X-rays is too high. The next from radio waves is microwaves, then infrared, ultraviolet, X-rays. That's the choice right there. B. Of the list, that's the best of the bunch. 2, according to Maxwell, light turns out to be a wave in the electromagnetic spectrum. It's called an EM wave, folks. Water? No. Light passes through a double slit, is viewed on the other side. The interference pattern is observed on the screen. Remember, the distance between, for maximums or minimums, it doesn't really matter. If you want to make the distance between them closer or smaller, you would need a smaller wavelength and a larger distance between slits. A smaller wavelength would be blue with a large distance between slits. The answer is obviously D. Hey, what type of wave is light? Well, it's a transverse wave, of course. And that's because of what we've seen in polarization. A Klingon spaceship is approaching Earth and shoots a laser out. How does everybody see it? Everybody sees light as the speed of light. 1c. Not too hard of a thing there. GPS satellites have atomic clocks on board. So what happens is you've got the Earth, you've got these satellites that are going around. They're going around pretty fast. I'm telling you now, they're not going near the speed of light. Just in case some people go, oh, they're going so fast, they're going near the speed of light. They don't go the speed of light. They are going fast, and as a result, time dilates and time ticks slower. But they're also further away from the stretching of space and time, the warping of space. It gets less and less, so the time speeds up because of general relativity. Time slows down because of special relativity. You could say there are multiple, that triangulate to your location to find you. There's an atomic clock on each. Each atomic clock is beaming a time, which then is interpreted to be how far away something is. I'm getting ahead of myself. 6 is B. It's moving fast, time slows down, and further from the Earth, so the time speeds up. 7. Which of the following is not related to Einstein's theory of special relativity? Period 2 had general relativity. I switched up, gave you special relativity. So special relativity includes things like the faster you go, the more it seems to dilate, distances change, time dilation occurs, E equals mc squared. The one that doesn't belong is gravity bending light. That's general relativity. B for 7, 8, in the photoelectric effect, increasing the brightness. So increasing the brightness just means more photons. The more photons that make their way down, the more electrons that come popping off of this. So again, period 2 had increase in the frequency. I gave you increasing the brightness just to see if you guys were paying attention. Increasing the brightness leads to more photoelectrons being emitted. C. What are the reasons for spectral lines? And that's because the electrons exist at different energy levels, and when they drop down, they release this energy in the as a photon of energy. 9 is C, and the constant effect is actually all the above. Electrons are ionized, so you have a wave come in, hits an atom, an electron goes off, and a longer wave comes out. So it has to do with conservation of energy, it has to do with electron being ionized. It's a momentum thing, and the wavelength emitted is larger, so all the above. I didn't think they were too bad, but that did hurt lots of people. Right, these short answers, you had to pick 3. I am looking for 4 points, but just not any points. Like for example, if you chose the first one, you said, oh, here's my 4 points. Newton believes light is a particle, and Huygens believes light is a wave. And Newton did not believe that light was a wave, but Huygens didn't believe light was a particle. 4 points. It's like, to me, that's a 1 point. One thought it was a particle, one thought it was a wave. Moving on. Next step. So you could say things like, maybe because they're particles and they hit heavier water, they get faster due to refraction, where waves would actually slow down. Maybe diffraction and interference. Newton didn't believe it because he didn't see it. Huygens thought it wasn't until Thomas Young's double slit experiment that we actually see light behave like a wave and show this interference and diffraction. That's kind of a key thing. CDs. If you pick the CDs, there are these tiny pits. They are a quarter wave deep. So that light goes there, light comes back, is now off by half a wave. When they meet up with a control wave that was created going through diffraction grating, otherwise known as a beam splitter, you get these two waves, and they can be either constructive or destructive. Constructive meaning everything is on, and you can, you call that a 1, or destructive, which is you're off, you get no light, it's your 0, which gives you your binary code. If you chose relativity, if you went with GPS, I've already kind of harped on it. With the Earth, you're fast, so time slows down. You're far, so time speeds up. Triangulating to different locations. They all have atomic clocks beckoning the time out. If you chose black holes, it's a collapse of a star that creates a singularity that warps space so much that even light can't escape. It creates this event horizon, the outer regions for which light cannot escape. You could say that as you get closer, time dilates, time seems to be moving slower. You can mention stars that go around will have their light bent. It can cause things like gravitational lensing. All these would make me happy. Quantum, you did the photoelectric effect. It should be that photons come in with a certain amount of energy. The energy might be enough to ionize an electron. If you send more photons, you'll get more electrons. If you send higher energy photons, you'll just get faster moving molecules. The flaws of the Ernest-Rutherford model. The Rutherford model looks like this. A charged particle oscillating around would basically give off electromagnetic waves. It should lose energy and spiral too. It's more than just, hey, look, they should spiral in. Why? It's because oscillating charged particles emit EM radiation. The other thing is, it doesn't explain the spectral lines. Why do we get a red, a baby blue, and these two purples for hydrogen? If electrons could be anywhere, but if you treat electrons like they were a wave, the electron is not just there, it's everywhere here. It's a complete wave in here. The first orbit, the second orbit, 2 waves, the third orbit, 3 waves, giving you very discrete. So A, it's not a charged particle oscillating, it's everywhere. And 2, now there's these discrete orbitals where the electrons could jump up and down and release photons of light. So I'm looking for 4 points there. The short answers look like this. In the first one, you're trying to find the angle and the slit separation. Whoops, X, M over L, whole waves. We are talking about bright spots. It occurs at 4 centimeters. You're 6 meters away. You're at the 3rd bright spot. The wavelength is 540 times 10 to the minus 9. D is what we're looking for. So with this, you can do some cross. You've already got that. You can also find sine inverse of this. By the way, your angle is very small, 0.38 degrees, and your distance is 0.000243, or 2.4 times 10 to the minus 4 meters. And we've got one more question. Tell me about red. Red has a longer wavelength, and that should bend more. Increasing this spreads it out even more. So for 4 marks, I was looking for those things. I didn't think that was too bad. This is a little harder, just, you've got air on a thin film on top of water. We're reflecting and we're seeing green. If you're gonna see it, you know it's constructive. Okay, so we've got A and B. A hits a denser medium. From here to here, that's a denser medium. B hits here, it also hits a denser medium. So they both switch by half a wave. A doesn't have any extra distance, and its total change is a half a wave. If this is going to be constructive, I need to make this a whole wave so that I get 1.5 and I can stay constructive. Another answer possibly is to go with 2 waves. Remember, the thickness is always half of there and back, so half of a wave is a half wave, and half of 2 waves is a full wave. Those are our 2 choices. You only have to do one thing left. You have to go N1, N2, wavelength 2, wavelength 1. In N2 and N1, this is 1.0. This is air going into 1.25. In air, it's green, 550. What is your new one? Oh, 440, sorry, 440. So half of that is 220, a full of that is 440. All right, those are your 2 choices, 220 or 440. I thought your question number 2 was easier than the other classes. I thought your question 3 was slightly harder than the other classes. So we have this length contraction equation, and we have this time dilation equation. It's just a matter where to put everything. So we're gonna go 99% the speed light. That is, by the way, 0.99 c squared over c squared. The c squares will cancel, but the 99 still is squared. Don't forget to put it in there. So 1 minus 0.99 squared. Now the spaceship just sitting there looks like it's 20 meters long. If you put your 20 meters there, your contracted length is 2.82 meters. Now the astronaut says 60 years ago, no, the people on Earth thought 60 years. So 60 years goes here because the astronaut's time is dilating and stretching. You have to find this time, and that regular time is 8.46 years. Okay? So 2 marks each, just getting down what you should be putting. Okay, so the photoelectric effect, I thought was a fairly easy question. You've got these photons coming in, so the energy they bring in, the energy of the photon comes in. You have to overcome the work function, and any extra energy is kinetic energy. So I gave you this information and this information, so no problem. The work function is 1.8, so it's 1.8, of course, times an electron charge. This is 2.88 times 10 to the minus 19. The kinetic energy, it's electron, 1 times 10 to the minus 31. It's going to 5.8 times 10 to the 5. Don't forget the squarage. You get 1.53 times 10 to the minus 19 for a total energy of 4.41 times 10 to the minus 19 joules. Right? So I should see you convert the work function to joules. I can see you calculating your kinetic energy. You put your total energy. It's the energy of a photon, which is equal to this or equal to this. I wanted the wavelength. So you're basically putting the energy down here and calculating the energy I get, or the wavelength I get, is about 450 nanometers. That would make it blue waves. But I made a mistake. I made a mistake. I left a question on that I intended to remove. And so I then ask, the moving electron, what is its wavelength? Well, wavelength of a moving particle is this equation here, and I know what the mass of an electron is, and I tell you that it's got a velocity already. All you have to do is plug that in to get 1.25 nanometers. So I made a decision and made this a 5-mark question instead of a 4, and your test is out of 43, not 42. The 5th question looks like this. You have this photon moving, and then it just magically turns into a positron and an electron that are both moving at 80% the speed of light. To know their total energy, mc squared all over a relativistic 80%, correct? 80% the speed of light will cancel. C squared, those will cancel. So you have to find the total energy, but just remember there are 2 particles. A particle makes out of an energy usually has a positive and negative sign, conservation of charge. So you have to put in 2 electrons here to get a total energy of 2.73 times 10 to the minus 13 joules of energy. And again, like the other problem, we want to know the photon's wavelength. Well, the energy of a photon is this. So the energy is this times this over wavelength. The wavelength is hc divided by the energy. So all you have to do is put in your Planck's constant and speed of light and divide by the energy provided by the 2 maturing, and you get, I think I've got this right, as 7.3 times 10 to the minus 13 meters long. Yeah. 4 lines. So remember, 5 of the, 3 more questions from this unit appearing on the exam next Tuesday. And as much as we were celebrating yesterday, all these people who got really, really good marks, there are others who need to pass the exam to earn the credit. So just take this so seriously. All good? Any questions on modern?
For the questions on modern physics on the exam, are they math questions or?
So the bulk of the exam is all mathematical. If there are any non-mathematical, it's usually a part B of a question. So find this and explain what happens if I change the frequency of the photon. You know, like a little added just to say, oh yeah, then they, not only can they solve for it, they understand the problem. You might see that a couple times through the exam. Not much, but there's never a question on its own that's just like, hey, like grade 11, tell me Newton's 3 laws of motion. Grade 11 had a write-out question. I really wanted to know because they knew how to do it. For us, energy and forces and all the units we've done, conservation you knew in grade 11, 3 body diagrams you knew in grade 11. Now I just want to see you tackle tougher problems. So a bulk of this exam is just some problems. Anybody else with a question on this one?
So I have a question regarding the exam.
Yeah.
I know there's some people that weren't here for some tests and you have to make a whole nother copy.
Yeah.
Are some of the questions from like the second copy going to be on there?
I would say that any test that I made, multiple versions of, to kind of keep period 2, period 4 honest, and those who came back the next day, none of them will look exactly like any of them. Like I'm not just pulling a question with the same numbers and things, but it's the same concept on all of those tests, so I picked the concept. So I might say, hey, if it's a double slit thing, right? It was easy for me for period 2 to say, you know what? I want them to work out this. I gave them this, the wavelengths at the 3rd nodal spot, and I gave them the distance. For you guys, I decided, let's make it this, let's not make it destructive, let's make it constructive. Who knows, the exam, am I looking for this now? Or am I looking for this? Like, I could go after something else. So it's not like, hey, I should study their test more than my own test. All tests are going to give you a sense of what's gonna be there. But then I will change it up and find something interesting about that. We'll go back to the test.
Like, for example, we didn't have airway on the test, would you?
We
like-
didn't have airwaves on the test. There is probably a lot more questions that I deemed more important in the grand scheme of things, that I decided air wedge isn't important enough to make my unit test. Is it important enough to make an exam? Your guess is? Cause I always told you your gut is probably pretty good.
No.
Yeah, my guess is that's what it is. Now, you know, there are some key concepts, like I really, in the end, what do we wanna walk away from, you know? So in the modern physics, what is it that I wanna walk away from? Is double slit an important piece of the puzzle? If you think yes, you know, a lot of hinges, even quantum of the electron relied on the wave nature of the electron. So maybe, just maybe, there's a double slit problem somewhere to be had. So you've gotta, when you go through unit by unit, and I can't answer, is this important? Is this not important to you? I'm not gonna, okay, Erwin, I'll give you a freebie, it's not on the exam. But I'm not gonna sit and analyze question by question, but this one. Cause you guys are cute, and you'll play this game, I know you are. What about this one, Paige? You'll hang around, bye everybody, see you. Okay, Paige. It's like, now that it's just us, you know, like me and your favorite students, can we talk kind of thing? So I will say no air wedge, but you know, you have to kind of feel like what's important. If you can't decide, practice it all, right? I only have 3 force questions, and yet we did Newton's laws, inclined planes, 2 body problems, we did equilibrium, we did circular motion. I have to pick.
So with the forces one, right?
Yeah.
I know in the like a different copy, like the second copy.
Yeah.
That people who weren't here for.
Yeah.
You gave them like an XYZ question with
Okay.
3 dimensions.
Yeah, all that would be forces, Newton's laws, break into components. If it's teaching the same thing, all those questions to me are free game, so I'd be prepared. I'd hate to say, you know, and you go, I don't think so, I'm not studying it. Like, all right, you're taking a chance. If you think, no, Paige taught us this, it's important, he threw it on somebody's test, should probably go over it. You'll notice air wedge didn't make anybody's test. First, second, I only have to do yours. So if it didn't make anybody's test, probably not.
I know you mentioned that before, there's not gonna be any like multiple choice, but for modern in the exam, modern physics, would there be any like?
Short answers
Yeah.
typed on the bottom, yes.
Okay.
We talked about it. It's out there. It's free game for me.
If I were to redo all of our tests,
Yes.
and then all of like your 2's tests,
Correct.
and then if I were to do the review, do you think I would be okay?
I would think you'd be in a really good spot. I mean, I filter down, I teach all this stuff, here's what's important on the test, I gotta filter down, and I'm not gonna just pick something from way out of the blue and say, they'll never see this guy, right? But having said that, it's never gonna look exactly like a test question. You're just getting into good habits, so practice as much as possible. Reviewing your old test is awesome, probably my #1 go-to is go over your old test, or several old tests, if that's what happens. I would then do the exam review, and if you're looking for more, go through sample problems I did in class, or pull out the textbook if you wanna do some practice. And again, chunk it up. I mean, I know we're not till a week, you know, we're not till Thursday, and today's only Wednesday, and you've got so many other exams before me, but if, as I review forces, if you think I can just do a little bit of forces tonight, you know, an hour just to practice. And if you feel really good about forces, you won't have to pour in lots of time. And I will be available the afternoon of the Wednesday to assist. Shall we do forces though?
the one unit that we did like an assignment instead of a unit test, are we gonna have that question or something?
Can't remember a unit.
It's like the
The rotational is not on the exam. Okay? To be completely honest, that's an AP topic, and as much as I would love to put it on, the important thing is, if I put it on your exam and it turns out to be a really hard question, and kids who did the 12U first semester go, our exam's so much easier than yours, I'll be encouraging more people to take this course rather than this course. So in the end, this exam looks very similar to this exam.
So what units are not gonna be just the rotation?
So rotation is the only thing that I did in the AP that I didn't do here. So everything else is fair game. So these students who say, well, your exam looks like, every test you wrote looks like mine. The only thing that you did was a one assignment on rotational, which counts for less than 1% of your final grade. I might as well have done the AP because I would have learned more stuff and be better prepared for university. So I'm trying to encourage people to try the AP. But you know what? If that pace, second semester where we lose a week, because exams are written early, and we lose a week because we did the rotational, you feel that pace is too much, take the first semester. It's going to be a little slower and a little bit more thorough, and you weigh that. But if you're up for it, I think there's huge advantages taking the APs. I don't want to scare you to say what. Unfortunately, I don't think chemistry, biology, or calculus are exactly like that. Fair enough. I don't know if taking the AP bio and the AP or the regular bio is the same or not. It should be close.
Will there be torque on the?
No torque, no rotation. Stay with us, Jonathan. We've been talking about all of this. We just want to confirm, I know. Equilibrium is in there, but without torque. Without torque. So Jonathan brings up a good point. I guess equilibrium is something, but without the torque. So we can still do that. Shall we? Alright, so in forces, I saw us do things like Newton's laws, where we said, hey, net force is equal to MA. And we kind of approached that. We talked about forces and their components, because in grade 11, my God, your boxes were like this, and everything was nice and simple. Life's not so simple, right? So we're going to take components into consideration. We're going to look at, inclined planes or things that are attached together. So these are stranger problems that you never saw in grade 11. So inclined planes, two body problems, equilibrium, which really is nothing. Couldn't handle in grade 11. And then there is the rotational or the circular motion. So when I say rotational motion, rotational forces. There is some rotation that wasn't part of that.
Was this like one of the questions where we could solve it with forces and energy? We like
You can
do
go with whatever you like. I mean, you will see unit 1, questions 1 and 2. Unit 2, questions 3, 4, 5. Questions, and if you say, I'm in unit 4, but I'm gonna still use forces to solve it, if it can be done, go for it. There's a little bit in field where you can do forces or energy. You'll have to use some of those prior knowledges for sure. So here goes. We'll start with one that has simple components. Let's take this box. Every time I do one of these problems, we're gonna go with a 50 kilogram box. Let's say I do pull it with 300 newtons at 30 degrees, okay? If I free body diagram it, there's got gravity down. Gravity is 50 times 9.8, 490 newtons. Normal up, hold on. This is not grade 11 anymore. The normal doesn't have to be 490. You break this into components, like this and like this. We notice this force here, sine of 30, which is a half. 150 newtons. This year, 260 newtons. I'm ballparking this, just spitballing as they say, okay? There is a force of friction. Let's say the coefficient happens to be 0.2. The normal, forces up have to equal forces down. So 490, take away this, 340. If I got 340 and I go by 0.2, that's 68 newtons. Well, this is a lot more than 68 newtons. In fact, it's 292 newtons of net force causing my little 50 kilogram box to accelerate, right? I'm doing X and Y components for this, and I would then put 50A in here and find it really close to about 3.9 meters per second squared. Does that make sense? So then we said, okay, you can do this, you can take forces, pull at an angle, find that, but what if the whole floor was an angle? What if we had an inclined plane? So let's just take a look at an inclined plane so you remember how they're done, okay? So blank slate, here goes, we got a box, guess what? The box is 50 kilograms, and I again am pulling at 500 newtons at 30 degrees. The ramp is only 20 degrees out, okay? If I free body diagram it, put a dot, you've got your gravity down, you've got this applied force like this, you've got a normal. Normals are always perpendicular to the surfaces. If it's sliding up the ramp, friction is down the ramp. I decide I'm gonna need some components. The applied force has X and Y components, but gravity too has gravity in the Y and gravity in the X. Just make sure the gravity in the X is parallel to the ramp, okay? And you don't go something like this and this across. What the hell is this? It's not an X component the way we like it. That's gonna cost you marks when you start to draw your free body diagram. So this angle here is 30 degrees, this angle here is 20 degrees. Let's go at it. 490, now I gotta do sine and cos. Sine is down here, cos is over here of the 20 degrees. So I'm gonna guess that this is somewhere around 80 newtons and 420 newtons. Somebody give me some answers here. Take 490 and go sine and cos of 20. This 500 newtons, I can tell you that this is for sure 250, and that this one here probably is 460 newtons. But if you want to go 500 cos of 30, you can double check those numbers. How am I doing so far? Anybody want to change a number? We're close? Close enough? Okay, let's just keep going then. If this is 420 and this is 250 and that goes this way, that goes this way, this one too should be something where we call this and this equal to this. So the normal plus 250 should equal to 420 coming down. So you're taking 250 away, you get 170, I think. That makes the coefficient 0.2, let's keep the same coefficient. 0.2 times that is 34 newtons. Now, pulling up the ramp, 460. Pulling down the ramp, yeah, 80 newtons down the ramp and 34 because of friction. We're only taking away 114 out of this. We're left with 346 as my net force. My net force is equal to MA. My 50 kilogram box here is accelerating really close to 7 meters per second squared. Again, this is just all quick numbers. You could do the math and practice it tonight or tomorrow or something. So we did some inclined plane. But then we said, what if a box was attached to another box and they're in together on this one. So I'll just do a nice simple one here. There's my box, it's the 50 kilogram, but it's attached to a 20 kilograms over the edge. Coefficient of friction is still 0.2. Just because this is 20 and this is 50, don't think it's going this way, okay? It doesn't go that way, it doesn't always go towards the heavier one. There's nothing really pulling it. So this is still gonna go this way. It's gonna have a tension, it's gonna have a friction, it's gonna have a normal, it's gonna have a gravity. Normal probably equal to gravity, 490. T minus friction is equal to MA. Friction is 0.2 of this, 98, 50A, which makes my tension 50A plus 98. On free body diagram, this going very, very fast. Over here, what's pulling it down is gravity, what's holding it up is tension, but I think gravity is gonna be bigger than tension, causing this mass to accelerate. It's only 20 kilograms. The force of gravity on it is 196. So T is equal to 196 minus 20A. The two ropes are the same, so 50A plus 98, 196 minus 20A. 20 comes here, no surprise, total mass is 70, is equal to 98. The acceleration is 1.26 meters per second squared, something in that ballpark. Okay, 98 divided by 70. 1.4. 1.4? Okay, 1.4. So we can do two body, we can do an incline, we can do two bodies on incline if you want to. But I'll go to an equilibrium. An equilibrium, that usually works, doesn't it? Nice. You're the first to catch it. As soon as I touch it, oh no. That's not. That's what happens to it, you just get so used to it. Okay, so equilibrium, let's put a box, let's dangle it by rope 1 and rope 2. Let's say this is, oh, I don't know, 50 kilograms. Let's pull it down, that's 490 newtons pulling it down. This one here is at 30 degrees, this one here is at 10 degrees. This has an X1, this has an X2. X1 has to equal X2. It's an equilibrium. There's gotta be no net force. Going up, this Y1 and this Y2 have to add together to equal 490, okay? So X1 is just basically force 1 or T1, and I would go cos of 30, T2, cos of 10. So T1 is just T2 cos 10 divided by cos 30. For that, I can get a number. That's about as far as it goes. Y1 is T1 sine of 30. Y2 is T2 sine of 10. And that's going to equal 490. But wait, T1 is T2 times this number. Anybody got a number?
1.137.
1.137, and sine of 30, so that's a half. T2 sine of 10, just out of curiosity.
0.173.
All right,
174.
let's go with 174. So half of this is 0.65 carry 1. I'm gonna go half of that. That's 6 carry 1, 8, something like that. T2 plus 0.174 T2s. Adding those together, 147 T2s is 490. Divide both sides by that number is your T2, and you go and solve. But equilibrium just says, hey, make sure everything left and right and up and down are equal. So it doesn't matter how you do it, whether it's a problem like that. I think this one came off of an assignment or test about spider web. That was a test question. So you look at that if you're looking for a test question sample. And so we did inclined planes, two-body, Newton's laws. The only thing I haven't talked about yet is circular motion. And anything going in a circle still needs some sort of net force pulling it towards the center of a circle. We've shown that the center acceleration is v squared over r, or you can go with 4 pi squared r over the period squared, or you can go with 4 pi squared r times the frequency squared. Those are on your cheat sheet. You can use them as you see fit. So one of the problems we looked at is like a star, a sun, whatever, and a planet going around, and just said the force it's pulling it in is gravity, g and 1 and 2 r squared, and that's keeping it in circular motion, maybe 4 pi squared r over a period squared. Because I know the Earth goes around in a year, so I can kind of tell you about its period. And mass of the Earth disappears, so it's mass of the sun that's in the middle. R is the radius, or basically how far apart these two celestial objects are. Next thing I did is I did vertical circles going around, but I said let's only focus on top and bottom, min and max. If you're at the top, some tension's pulling it down, gravity's pulling it down, tension at the top. At the bottom, the tension is up, but the gravity is down. Tension at the top plus gravity is the net force. Or bring that over and you subtract mg. T at the bottom minus gravity is your net force. Bring this over and you add mg. You'll notice the tension at the bottom is bigger than the tension at the top. And there are problems when the tension at the top really get close to 0 when you go your slowest possible speed. Any slower and you'll fall out of these orbits. Then we did a lab, we said here's a little, basically pipe, and you've got a string to a rubber stopper hanging from another mass. Let's say this mass is 500 grams or half a kilogram, with gravity being 4.9 newtons pulling it down. Well, tension holding up is 4.9 because this is in equilibrium. It's just hanging there, just like this, nothing happening to it. All the force is equal. And because they're all one string, this is 4.9 newtons. If you know the mass of the rubber stopper, let's say 20 grams times 9.8, 0.196 newtons, you can tell me that this T in the X and T in the Y. T in the Y has to equal this. And you know T. So if you know those two, you find Tx. Tx is what's causing it to accelerate towards the middle of the circle. So if you know what Tx is, you can go find the speed or the frequency at which it goes around. So we did planetary objects, flat, almost no gravity at all kind of thing. Not that any gravity is tipping it down. We did vertical circles, we did horizontal circles. We talked about how things go around held on by friction. If friction is your only thing, friction is your net force, and you just go and solve coefficient times normal, MA. Coefficient is mg equal ma, no problem. Coefficient is a over g. That equation's on your cheat sheet. Go ahead, just use it if you want to. Anybody have anything they'd like to see on the forces unit? I do want to give you about 25 minutes if I can. Sean, what do you got?
How do you find the velocity at the bottom?
The velocity at the bottom here?
Yeah.
Okay, so depends. I mean, the tension at the bottom is ma, which is v squared r plus mg. So it could be that I do something like at the top, where the top is ma or m v squared r minus mg, and I say, guess what? The tension at the top is near 0. Find the velocity. Assuming it's moving with uniform, like a constant speed, not uniform motion, but constant speed, and if you carry that velocity down to here, find the tension at the bottom. Could be a problem like that. Does that make sense? I've done roller coaster problems where in a roller coaster, you have to realize that as you come down, you actually speed up because of conservation of energy. So I've done that before. where, okay, you're going this fast at the top, you'll pick up speed on the way back, what's your normal at the bottom? You have to kind of say, well, my kinetic energy, my potential energy adds to the kinetic energy. Anything else you'd like me to see or do or chat about that might help you prepare? I know it's a long way away. Some of you are drifting on me. I can't believe it. I'm giving you questions that represents 40% of your final. And it's like, no, not today, just not interested, not into it. Get into it, folks. You know, even for 30 minutes, just do it and then be done. I'm going to let it be then. Go for it, work on it, do something.
No, we have it.